Deung-Jang got her PhD in 2012 from the University of Strasbourg in France. She worked at the Ewha Women's University in Korea, at MIT in US, and at the Max Planck Institute for Structure and Dynamics of Matter in Germany. And she was an Alexander von Humboldt Research Fellow and a Marie Curie Research Fellow. And right now she's a Annika Vázquez Research Fellow in the Material Physics Center in Spain. Her research is focused on atomic devices on superconductors, and in particular, how we can make some steps towards topological quantum computing in these devices. And today she's going to tell us about atomic spin structures on surfaces. So we are really looking forward to your talk, and please go ahead.
So hello everyone. First of all, thank you Peter and Jose for having me in the atomic scale quantum material colloquium series. So it's great that you continue the series this semester as well, so we can continue enjoying many talks. So thank you. And it's a bit awkward to give a talk without looking at you, but I will do my best. So it's very nice to be connected with you and happy to give a colloquium. So my name is Deung-Jang Choi, mostly I'm called DJ and based in San Sebastián, Spain. So today I'd like to talk about the atomic spin structures on surfaces using a scanning tunneling microscope. So we would like to develop the devices with a function that make use of this quantum. So quantum properties such that they will permit us to develop new paradigms and new technologies. So to achieve this, atomic spins are very interesting because they are fundamentally quantum. So atomic spins are discrete and present quantized energy levels, and they can be entangled with the other spins such that the value of one spin depends on the value of the other spin. And they further shows this, they further present these non-trivial many-body correlations that transcend simple theoretical predictions. So all these properties lead to the exciting possibility of performing the complex quantum operations by manipulating spins. So putting them on a solid interface and creating a device is a necessary step for developing quantum technologies. So then interesting strategy is to use this atomic spin with solids, particularly on interfaces such that solid can be modified and accessed from the microscopic scale. So spins on surfaces become of great interest for technology in addition to their intrinsic scientific interest. So the atomic spins can easily find application in spintronics. So spintronics is a technology based on the spin rather than a charge of the electron to transfer and manipulate the information. So tantalizing example of spins on surfaces in spintronics are this first demonstration of all spin-based logic gate by Alexei Kazacharian and co-workers in the San Damas group, and another very tiny small memory unit based on the iron 8 atoms on kappa nitride surface by Sebastián and co-workers in English group. And the another promising field of application is the quantum communication. So many theoretical examples predict the transmission of information along atomic spin chains with great fidelity. So here you see the examples of quantum communication using a quantum mechanics to encode the information and transmit it. So these Banchi and co-workers have shown that this quantum fluctuation in a spin system can actually uses a small external magnetic field to tune the given quantum phase of the connecting spin chains. And in this way, we can control this transmission of the information. So here the value of the spin on the source can be transmitted along the spin chains with a coupling J among these spins. And the third example of application using spins on surfaces would be this quantum computation. So thanks to the manipulating the time-dependent evolution of spins, it is now possible to perform active operations between spins that are needed for quantum computation. And another strategy is one of the topological quantum computation by braiding these Majorana fermions on superconducting surface at the edges of this spin chain. And one more application is this quantum sensor. Electron spin resonance with the scanning tunneling microscope opens up the door to the measurement of tiny amounts of energy, detecting the minute interactions. So based on these interests, we are studying the spin zone surfaces using a scanning tunneling microscope. So with the STM, we can do many things. One of them is to move the atoms. So to construct the nanostructure, atom manipulation can be done by applying a voltage bias to pick up the atom and drop them off where we want to build the nanostructures. So here, this is the example of the atom manipulation with these iron atoms that we built 2x3 iron atomic arrays on the this copper nitride surface. And another thing that we can do with the STM is measure inelastic tunneling spectroscopy. So basically, when we are sweeping the bias between the tip and the surface, we get the elastic tunneling signal. But once we apply the bias needed to excite the magnetic energy level from ground state to the excited state, then we can open up the additional conductance channel and get the one more signal. So we get the additional signal from this inelastic tunneling. So by measuring this ITS spectra, we can map the discrete energy level of your system. So here you see this example of this ITS spectra measured on a single iron atom on copper nitride surface. So by measuring it, you can see that how the energy levels are aligned in your energy diagram. So today my talk will be about the atomic structures on 3 different systems. So first topic will be the exploration of the new properties of spin structures on solid surface. So we build a new complex Kondo system composed of the non-Kondo impurities. And the second topic will be using quantum and many-body effects as the hybridization of in-gap states in superconductors, where the in-gap states are produced by the atomic spins on superconducting surface. And the final topic of my talk will be to go beyond the atomic spins to molecular spins and use the flexibility of molecular chemistry and binding to create the complex non-collinear spin arrays. So let's get started with the first topic. Before that, let me briefly explain you what the Kondo effect is. So Kondo effect is shown when you embed the magnetic impurities in a metal. So due to this interaction between the magnetic impurity and this conduction electron in a bath, basically this magnetic moment of the impurity is screened. So the new electronic ground state appears as a consequence of the electronic correlations induced by the impurity, with the fact that the total magnetic moment of the system becomes 0. So when you look at the density of state of this magnetic atom, you see that the new state appears at the Fermi level, and the peak is given by this 2kV TK, and this TK is the Kondo temperature given by the energy needed to destroy this many-body Kondo ground state. So this Kondo temperature is given by this epsilon, which is the energy position of the magnetic energy level, and gamma, which is the broadening of the energy level due to this hybridization with the substrate, and this Coulombic present U. So now in our study, we use these iron and manganese atoms on copper nitride surface on copper 100 crystal. So here you see we have this energy level of this manganese atom on copper nitride surface. So manganese atom basically behave as a spin 5 health system, and this easy acyl anisotropy presents a doubly degenerate spin plus minus 5 health ground state. And a spin flip process from the substrate atom can only transfer 1 unit of spin. So the the plus 5 health spin ground state cannot flip into the minus 5 health and vice versa. In other words, this Kondo process is not possible here. So when you look at this differential conductance measurement measured on this single manganese atom on copper nitride surface, you see there's no Kondo effect. Instead, you see the small gap. So this small gap is due to this excitation of the plus minus 5 health ground state into this first excited state plus minus 3 health with a very small anisotropy energy of this manganese atom on copper nitride surface. And for this iron atom, a single iron atom presents the spin 2 system. So the presence of these both longitudinal and transversal anisotropy mixes up and splits up the spins here. So the conductance shows basically the 3 steps from the ground state to this first 3 excited states. So So here basically you see the only the excitation inelastic tunneling spectra, and there's no Kondo peak. So that's because when you look at the ground state, they are not degenerate, that they cannot make the Kondo effect. But when you combine this iron and manganese atom together, and you can form the dimer, and if they can couple antiferromagnetically, then they can have a spin 1 half system. So then this can have the degenerate ground state that can be connected via the spin flip, delta M equal plus minus 1. So then we can have this Kondo effect. Sorry. So here, when you look at this DRV spectra, there is a clear zero bias peak as a signature of this Kondo effect. And we can understand this conductance behavior if we assume that the two atoms are coupled antiferromagnetically. And since this manganese atom has a very small anisotropy energy, this first excitation is approximately coming from this spin flipping of the manganese spin in 1 unit. So this leads to the change in the Heisenberg interaction between the manganese and iron atom, giving rise to this first step here. So the smallest chain we can build is a dimer, and now we can extend our structure to be longer, starting from this iron manganese dimer up to iron manganese 10. So you see here the DIDV spectra measured from iron manganese dimer up to iron manganese 10 chains, and you see clearly this even and odd number odd effect. So due to this change of the ground state. So basically, when you have an odd number of manganese with the iron chain, the total ground state is spin 1 half. But when you have this even number of manganese with the iron chain, the total ground state is 2. So basically, when you have an even number of manganese with the iron chain, you can see this Kondo peak at the Fermi level. But when you look at the even number of manganese with the iron chain, there's no Kondo features appearing. So to see the spatial distribution of the conductance feature in the chain from iron manganese dimer to iron manganese 10, we measure this spectra along the chain. So here the bias is plotted in each x-axis, and the y is the position where the spectra were measured. So you see that the spectra were taken, and this color code shows this DIDV signal intensity. So you see that the Kondo peak appeared along this even other number of manganese with the iron chains, while for this even number of manganese with the iron chain at the Fermi level, you see that there's no Kondo features. So the interestingly, when you look at this other number of manganese with the iron chain, this Kondo peak intensity actually gets stronger when you move away from this iron atomic site. So even though we do need the iron atom to be able to have a spin 1 half ground state, actually this Kondo peak intensity gets stronger when you move away from this iron atomic site. So this study points out that the strong entanglement of the spin creates a new spin state, and free system changes its magnetic character. So the role of this entanglement can be more clearly seen here when comparing this manganese 3 iron chain with the iron 3 manganese chain. So we found this qualitative different behavior despite the fact that they have a same ground state of 1 half. So both cases, the ground state is still degenerate and can be connected via a spin flip, resulting in these Kondo correlations. However, only the manganese 3 iron chain shows the Kondo effect, and iron 3 manganese presents no Kondo peak, and excitation gap is even bigger. So the magnetic states at play are clearly different here. So the explanation of this behavior can be traced back to the presence of this magnetic anisotropy in the chain. So the magnetic anisotropy is small for the manganese and then large for the iron atoms. So as a consequence, the spin in this iron manganese 3 chain, it is more free to flip the spin than this iron 3 manganese chain. So we can expect a very different degree of entanglement in these two chains. So here you see the wave function degree of entanglement in the two chains here. So here you see that the spin wave function composition of this one of the two degenerate ground state. So the greener the color is, the larger the wave function coefficient for that spin component is. So from this graph, you see that the iron 3 manganese chain has one very large component, making almost perfect antiferromagnetic yield state. While for this manganese-3 iron chain, the color contrast is less dark, showing a large mixing of these spin configurations. So therefore, the spin flip transitions are more easier to take place for manganese-3 iron chain than the iron-3 manganese chain. So you see clearly here the...
DJ, sorry for interrupting, but there's a question in the chat by Thomas Susi. So he's asking, how is one sure about the chemical identity of each atom? Is the atomic local density of state sufficiently distinct? Sorry if I missed this earlier.
Sorry, I don't hear you well.
Oh, so
can you repeat, please?
Thomas asked, how is one sure about the chemical identity of each atom?
How we can identify each atoms?
Yeah, how are you sure about the chemical identity of the atom? You can perhaps look at the question in the chat.
Yeah, we can put the atom one by one, right?
But you have to start with known atoms, right? So for isolated atoms, you use the LDOS signal to say that this is manganese, this is iron, and you compare to a DFT simulation, presumably, or how does this identification work?
So here, you're talking about this wave function?
No, even much more fundamental. So you have a surface, and you have manganese atoms, and you have iron atoms. How do you know which atoms are manganese and which atoms are iron?
That is very easy with the SGM. So you can identify first with the manganese and iron features for single atoms. So when you manipulate the atom, you always train the tip in a way that you pick up the manganese atom and drop it off before really making the chain.
Right, and the signature here you compare to a DFT simulation or something to know exactly which atom gives which signature.
Here, I don't show any DFT calculation.
But so any LDOS signature is just an LDOS signature. It's a spectrum. And how do you know what spectrum comes from manganese and what spectrum comes from iron in the first place?
So your question is how we can make sure that when we build the nanostructure, whether that is manganese side and the iron side?
Just even more fundamental, when you deposit your atoms to the surface, how do you know which atoms are manganese and which atoms are iron? Because you don't have direct chemical sensitivity in STM. So presumably you have a signature in the DIDV, but how do you know what signature is which atom? Is this based on a DFT simulation?
No, this is experimental fact that you put on the manganese atom and then you can see these features when you are measuring on the manganese atom. So this is the differential conductance measurement, right? So you can really identify which one is manganese and which one is iron atoms.
Right,
so
based on what? You know, a signature is a signature. You have to identify, connect that signature with a chemical element somehow, right?
Okay, maybe I can interject here. So I think you just evaporate iron, so you have nothing else than iron, then it looks like this. Or you just evaporate manganese, and then it looks like the other spectrum. So I mean, you know which atoms you are evaporating, right, DJ?
Yes.
Okay, thank
you. Yeah. So with the SGM, you can really identify each atomic features by measuring this differential conductance, and you can identify. So if before mixing up with the iron and manganese atom on the surface at the same time, you can only evaporate manganese and then characterize, and you can only evaporate iron and characterize. And they always show these characteristic features that shows all the time 100% same for manganese and iron.
Okay, so it's not based on a modeling. Okay, thank you.
No. Okay. So, yeah. I was here, yeah. So you see, this is the transition probability between these two degenerate ground states at each atomic site. And it shows clearly that the transition probability gets higher when these manganese atoms move away from this iron atomic site, which is in agreement with this larger Kondo peak. So from this study, we learned that this entanglement of the spins in the chain make it possible to have a spin flip transition induced by the substrate electrons that lead to this Kondo effect. And by assembling these non-Kondo magnetic impurities in a heterogeneous way, the new spin object appears and shows the Kondo effect. So this is the emergent phenomenon where a new property is found, and this is coming from this collective behavior. And the chain we have built allow us to show the spin entanglement extending over 4 nanometers. So now let me move on to the next topic involving the spins on superconductors. So when you look at this density of states of this superconductor, all of these single particle states are occurring above this delta. So delta is the energy that you need to pay to break this Cooper pair. And this breaking Cooper pair can be expressed as this Bogoliubov quasi-particle excitations. So when you break this Cooper pair, in other words, creating a quasi-particle, you can create the 1 electron, and at the same time you annihilate the electron, meaning you create this hole. So this quasi-particle excitation then becomes this 2-component excitation with this electron and hole, meaning that creation of this electron with a wave function u, and the creating the hole with the opposite spin and wave function v. Now we can make a similar excitation by putting these magnetic atoms on this superconducting surface. So when you put this magnetic atom on superconductor, the magnetic atom can locally form the magnetic field. That this locally formed magnetic field can weaken or break this Cooper pair, so they can make this. They can create this. They can make this excitation of the quasi-particle. So as a consequence, 1 particle states are occurring inside of the superconducting gap. So we call this localized bound in gap states as so-called the Yushiba-Roshinov states, and Yushiba-Roshinov states. And this excitation then can be expressed as this creating the electron with the wave function u, and at the same time creating the hole with the wave function v. So this energy position where these localized bound states are occurring, the Yushiba-Roshinov state is given by this J, which is the coupling strength between the magnetic atom and the Cooper pair. And once this coupling, the interaction gets really strong, then magnetic impurity can eventually break this Cooper pair, that this magnetic atom can capture 1 electron from this broken Cooper pair, forming a new singly ground state. So by changing the ground state from the doublet to the singly ground state, we can have the quantum phase transition. And since this J gets really bigger, eventually these in-gap states, in-gap YSR states, can cross the Fermi level. So this wave function for this electron and hole components are reversed. So now in our study, we are using this superconducting chip to increase the energy resolution. So when we employ a superconducting chip to measure the superconducting gap of the sample, so at the positive bias, we are detecting the empty states of the sample, meaning that the electron side of the quasi-particle tip appearing at the 2 delta. And in negative bias, we detect the occupied states of the sample, so we can detect the whole side of the quasi-particle tip appearing at -2 delta. So by employing a superconducting chip, when you detect the superconducting sample, you will see that the quasi-particle peak appearing at ±2 delta instead of at the 1 delta. So now we can use a superconducting chip to detect these YSR states. And since we are measuring at certain temperature, meaning that we have a certain degree of Fermi-Dirac distribution. So in other words, that means that we have a little portion of occupied electron components of the YSR states, as well as the little portion of unoccupied whole components of the YSR state. So when you see the positive bias, you will detect the empty states of the sample. So first, you will see the little portion of whole components of the YSR states appearing at delta minus epsilon b. And when you see further, you will detect the electron components of the YSR states occurring at the delta plus epsilon b. And then negative bias, we are detecting the occupied states of the sample. So first, you will see that little portion of occupied electron components of the YSR states occurring at minus delta plus epsilon b. And when you see further, you will see these whole components of the YSR states occurring at minus delta minus epsilon b. So when we are employing a superconducting chip to detect these YSR states, we will see at the plus minus delta plus minus epsilon b instead of at the plus minus epsilon b. So for the study of single spins on superconducting surface, let me show you the study of these chromium atoms on the lead-1 surface. So here you see this topographic image of the chromium atoms on lead-1 surface. So the DFT calculation found out that actually the chromium atoms are embedded into the surface, having these octahedral-like structures, hybridizing with 7 nearly lead atoms. And we have performed the IDB measurement with a superconducting tip to increase the energy resolution. So on their surface, it shows a nice superconducting gap at 2 delta, which is about 2.7 millivolt. And on chromium atom, it shows these many in-gap states. So the total, we found 12 peaks, but since we are using a superconducting tip, we need to deconvolute the IDB from this tip sensitive state to have the information of the on the actual YSR states. So by deconvoluting these BCS sensitive states fitted to the superconducting tip, we obtain the 5 pairs of the YSR states for the electron side and the hole side. So this points at the 5 different scattering channels of the magnetic impurities. So the question is then now what these scattering channels are. So from the DFT calculation, we obtained that there are 5 populated d orbital of these chromium atoms lying below this Fermi energy around the 3 electron volt. And they are singly occupied, then they can be perfect spin scatters. So each 5 orbital can be perfect spin scatters. So these states will give rise to a different J depending on the hybridization of the chromium D states with the lead states. So to see the spatial distribution of the YSR states, we perform this DIDB map over the chromium atoms on the lead-1 surface. So here you see the DIDB maps at different bias where the YSR states are occurring. And the experiments were performed at 1.2K. So this leads to a certain population of these states below and above the Fermi level. So that produces these duplicated peaks at the positive bias and the negative bias below this delta. So you see here that this peak is some replica of the first electron side of the YSR states. And this is the some replica of the first hole side of the YSR states. And this is very well, this behavior you can see very well here, this DIDB map, that this peak is basically the some replica of this peak. And this is the some replica of the whole side of this YSR state. So basically now this is the reason why the 5 pairs of the YSR states lead to these 12 states in total using a superconducting tip. So now we want to see that why we have this non-equally equally distributed YSR states over this chromium atom. So to understand why we have this behavior, we calculated this wave function based on the 5 orbitals that they are forming here. The Cooper pairs are weakened by this magnetic interaction from each of the 5 orbitals. So in our first approximation, we could expect that the scattering potential will have a spatial distribution following the shape of the scattering orbitals. So this would lead to the this would lead to these images shown here based on the wave function of each orbitals here. So by comparing the shape of scattering orbital with the DID maps, we can see these considerable differences. So there are still missing features. So what we did is that basically by solving this Bogoliubov-Lujan equation, we found actual quasi-particle wave functions for the electron side and hole side. So based on these 5 orbitals, we calculated this, we simulated the Shiba states for the YSR states for the electron components and the hole components. And you see that the different features of these simulated YSR states are appearing based on these 5 orbitals that they are forming. So now when we compare theoretically simulated these YSR states with the experimentally obtained DID maps, we find this qualitative agreement. And from this work, we managed to visualize this orbital contribution of the YSR states by measuring these DID maps. So for the next study, we used the type 2 superconductors, such as this beta bismuth 2 palladium superconductor. So bismuth palladium is a BCS-like superconductor with a gap of 0.75 millielectron volt. and it presents the bismuth-rich square surface. So the large value of this spin or coupling of bismuth plus this layered structure of this material leads to a large values of a Lashba coupling. So we deposited chromium atoms on this bismuth palladium superconductor and got very nicely isolated chromium atoms having halo position as the observation site with a spin 5 half. And we have used the bismuth palladium coated superconducting tip. So our DIDB spectra on their surface shows a superconducting gap at 2 delta, which is about 1.5 millivolt. And when you measure on this chromium atom, we have one pair of the in-gap states. So by deconvoluting a superconducting tip, we get a nice BCF features on their surface and the YSR, one pair of the YSR states on the chromium atom. Now here, I also want to point out that the comparison with this deconvoluted spectra measured at 1.2K using a superconducting tip and the DIDB spectra directly obtained at the dilution-free temperature using a metallic tip shows nice comparable results. So it shows very nice clear sharp quasi-particle peak here on bare surface. And this one was measured at millikelvin SCM that is working at QNS. So this allows us to study the superconducting system using a non-superconducting tip. So interestingly, it is feasible to manipulate the chromium atoms and build the spin structures. So this allows us to build different types of the chromium chains and study their effect on the in-gap states. So here you see the example of these built chromium chains. So first, to understand the magnetic interaction between the two magnetic atoms, two chromium atoms at different distances, we created differently spaced dimers here. So depending on the spin coupling between two atoms, we expect to find different in-gap states. So before going into that, let me explain you what happens to YSR states in this coupled dimer. So in the case of these antiferromagnetic coupled dimers, each atom has a YSR state, and since they are anti-aligned, YSR states cannot hybridize, meaning that basically the YSR states are localized into each magnetic atoms. So so this tells us that this antiferromagnetic coupling leads to localized in-gap states, in-gap excitations into each magnetic atoms. However, if coupling is ferromagnetic, the YSR states have the same polarization aligned in a parallel so that they can hybridize each other. So they can form these hybridized YSR states like the molecular bonding, anti-bonding states. And then it can split these YSR states into two peaks. So they are basically forming this anti-bonding, anti-bonding like states that they can split this, they can split the YSR state. So here you see the DIDB spectra for each chromium dimers at different distances, and you see you find these distinct features. So the gray curve were measured when they're in a single chromium atoms, and red curve were measured after putting second chromium atom at different distances. So first, you see when you have this square root of 5 unicell apart dimer, you see that the YSR states gets weaker. That means they start to interact each other. And these two unicell apart dimer, you see that the Shiba states, or the YSR states, are moving towards to the quasi-particle peak. And eventually, when you have a one unicell apart dimer, the YSR states disappear. And when you look at the square root of 2 unicell apart dimer, it shows the split YSR states. So this is the deconvoluted DIDB spectra. So you see for square root of 5 unicell apart dimer, the YSR states gets weaker, and the 2 unicell apart one, the YSR states are moves towards the quasi-particle peak, and eventually for 1 unicell apart one, it shows no YSR states. So this gives us a hint that actually they couple antiferromagnetically, that the magnetic moment is screened, that eventually when you have a 1 unicell apart dimer, the total magnetic moment becomes 0, that it shows this no YSR state. While for the square root to diagonal unicell apart dimer, it shows the split YSR states, meaning that they couple ferromagnetically, that they are forming bonding anti-bonding like YSR states, showing these split YSR states. So solving the Bogoliubov-Deung equation for anti-ferromagnetically coupled or ferromagnetically coupled dimer, it shows this very different behavior. So single states are shown for this anti-ferromagnetic case, while for the ferromagnetic case, it shows this complex split YSR states. So the spatial distribution of the DID measurement clearly shows how they couple magnetically. So this is the line spectra that we measured along this 2 unicellular dimer along this direction. So this is a high profile along this line. And you see that this is the voltage bias that we apply and the position. So you see that inside of the superconducting gate shows the Shiba states, YSR states. And when you map the states at the electron side and the hole side, you see clearly that the basically YSR states are localized into each magnetic atom without any hybridization. So this tells us that they couple antiferromagnetically, having no hybridization of the YSR states. Basically, these states are localized into each magnetic atom. While for this diagonal square root 2 unicellular dimer, so it's again the line spectra measured along this direction. So this is the high profile along this line. And you see that inside of the gap, it shows the split YSR states. And when you map the states for the inner peak, it shows nice bonding state. And then outer peak, it shows nice anti-bonding state. So this tells us that they couple ferromagnetically, that it's showing split YSR states. And as well, it shows this bonding, anti-bonding like YSR states. So, and to finish my talk, I'd like to use a more complex impurity than a single atoms. So now the third topic of my talk is the use of these molecules to create the non-trivial spin structures on surfaces, in particular on superconducting lead-1 surface. So we use this nickel-leucine molecule. This molecule has a clear molecular aces that joins these two cyclopentadiene ligands and nickel atoms. So the nickel atom is in the 2+ oxidation state with the D8 configuration, such that there are 2 unpaired electrons leading to the molecular spin of 1. So a single molecule binds by 1 cyclopentadiene to the surface, leading to this donor STM images due to this contribution of this DXG and DYG orbitals to the electronic energy close to the Fermi level. So the molecule has the E-plane magnetic anisotropy, and the ground state of the molecule is M equals 0. So the two excitation to M equals +1 and M equals -1 take place roughly at the 3.8 millivolts, as can be seen in the step of this ITS taken on the molecule. So there's no need to decouple this nickel spin from the substrate because this molecule protects the spin. So the data shown here have been taken on the kappa 100 surface. Now we deposited these nickel-leucine molecules on the lead-1 surface, and we found the structures in 2 different ways, zigzag and the paired nickel-leucine layers. So paired nickel-leucine layer forms in two ring shapes, basically a dimer of nickel-leucine. So let's have a look at the DID spectra for this paired nickel-leucine layer. So here you see the DID spectra measured on the different molecules of this paired nickel-leucine layer. So between the -15 to 50 millivolts, we found some characteristic features. So the tip is again here superconducting, that the gap is appearing at the ±2 delta. And you see corresponding these quasi-particle peaks obtained on the different molecules on this paired layer. And their peaks are at the same energy, the 2 delta, regardless of the molecule, the position where the spectra were taken. So regardless of which molecules are measured, the quasi-particle peaks are appearing at the ±2 delta. However, here the next displaced by the 3.8 ITS step, we found the replica of these quasi-particle peaks shifted by this inelastic step of the nickel-leucine, M equal 0 to the M equal ±1 transition. So as is well known for nickelocene, the inelastic conductance is several times larger than the elastic one, leading to a strong enhancement of these quasi-particle peaks. So let us zoom in these peaks. Then the contrary to these quasi-particle peaks, the ITS shifted peaks do present a dependence on the peak position on the place where the spectra were taken. So the ITS peaks largely shift into two different bias, mainly at the 6.1 millivolt and 6.6 millivolt. So this can be explained if the molecules are different on the substrate, but surprisingly, the topographic image shows the identical environment for each molecule. So here on the left, you see this constant current topographic image, where in principle, all the molecules see a comparable environment. And we measure the conductance mass at different ITS steps, namely at the 6.0 and 6.6 millivolt. And we clearly see that the molecules are not equivalent and that there are clear patterns appearing depending on the applied bias. So we performed the DFT calculation using a spin-off coupling to study this magnetic anisotropy dependence of this absorption site. So for the four high symmetry absorption site of the molecule on the surface, namely the FCC, bridge, and top HCP, we found the shift as large as 0.4 milli-electron-volt difference between the top and the HCP site, while for the FCC and the bridge present the same anisotropy. So when we study the monolayer, we realized that there are other type of nickelocene molecule. So nickelocene with the molecular axis lying parallel to the surface, call it as a line molecule or horizontal molecule. So this molecule cannot be seen in the SGM image, then we cannot measure the VID spectra. But the line nickelocene molecule can be guessed from this low bias constant current image. So this is in good agreement with the previous experiment on this kappa 100 and kappa 11. So the molecular structure is due to the van der Waals interaction among the molecules. So the round here presents the standing up vertical molecules, and these two triangles shows these lying down horizontal molecules. So this is the result of this our non-collinear DFT calculation, and we found several interesting facts here. That first, these vertical molecules, they sit on a different absorption site, explaining the anisotropy dependence of the seemingly equivalent molecules. And second, this vertical molecule, these standing up molecules, they are coupled ferromagnetically, while for this laying down molecule, they couple antiferromagnetically. So this can be seen nicely here in the side view. So the difference in ordering can be traced back to the type of the interaction between the molecules. So the vertical molecule here, presents the non-negligible this hybridization with the substrate. So this can be seen clearly that this projected density of states calculation here for the molecular states for the vertical molecule nickelocene and the horizontal nickelocene. And we see clearly that for the vertical one, it shows the broader peaks and the shifted in the energy presenting a small charge transfer. And it shows the large interaction with the substrate compared to this horizontal one, which shows very nice sharp states. So as a consequence, this vertical molecule can interact with the substrate via, they can interact via the substrate like Ikeikawa interaction, having the, showing this ferromagnetic coupling. However, for this horizontal one, it shows they can have this overlap, some overlap via these cyclopentadiene rings that they can have the super exchange like antiferromagnetic interaction between these nickel spins. So due to this important exchange coupling between the molecules, we can expect to have a collective.
There's a question by Thomas Susi about what is the DFT functional that you used there, and whether you included van der Waals interactions.
Yes, we included van der Waals interaction because the molecules basically they couple, the interaction is based on this van der Waals interaction, And the first question was?
And which functional did you use?
Which function?
Functional, like DFT functional, exchange correlation functional.
Oh yeah. This is non-collinear DFT. DFT. So they include this non-collinearity.
Yeah.
In the DFT calculation.
That doesn't quite answer the question. So which exchange correlation functional?
Which exchange correlation?
Yes, the functional PBE. Then there are van der Waals functionals, LDA. You know, which functional?
I think here it's van der Waals, but yeah, this DFT calculation was done by theorists, so I can confirm it. But as far as I know, it's van der Waals.
Yeah, but there are many different van der Waals functionals, and they might have slightly different effects when you're looking at very subtle energy differences between absorption sites. But okay, if you don't have the details, that's fine.
Yeah, and there's another question by Christian Matt, which is if you can do spin polarized STM to confirm this P alignment.
Yes, so actually we are planning to do the spin polarized STM on this system. So this is the ongoing work that we are working now. So yes, that is planned. Okay. So yeah, let's continue. So due to this important exchange coupling between the molecules, we can expect to have a collective response of the molecular spin. So this leads to the spin wave function in the molecular layer. So we can expect that the local spin excitation is coupled to the collective spin waves, leading to the intrinsic lifetime of the local excitation. So basically, this excitation can translate into this broadening of the local spin excitation. So experimentally, we compare this ITS peak with this quasi-particle peak that we measure. And we expect that they have a comparable width because they share the instrumental broadening of the measurement. However, our experiment clearly shows that there are extra broadening of the extra broadening when you compare the ITS peak with this quasi-particle peak. So when the same measurement was done on the lowly coordinated disordered molecules, we found that the broadening of the ITS peak and the quasi-particle peak, they show the similar broadening. So this behavior hints at the presence of this some collective spin wave excitation in the paired nucleosine layers. So from this study, we found the molecular template of spin texture on superconducting surface, where it can lead to the exotic topological properties. So to summarize and wrap up the today's talk, so we create the new functionalities from the spin zone surfaces. So first part, we emerge Kondo effect from the non-Kondo impurities. So spin chains with the different atomic species give an extra knob to tune the functionalities. So in this case, I talked about how we can create the Kondo correlated spin chains from this iron and manganese atoms that do not present the Kondo effect themselves. And second, we manipulate the electronic states in a superconducting gap. So YSL states and the new states appear by associating the more impurities. So I show you that the same surface can have the antiferro or ferromagnetic coupling on this bismuth palladium surface thanks to the geometry of the spin structures. And the last part, we use molecules to create the complex non-collinear spin structures thanks to their chemistry. So this can have a potential, potentially important consequences, for example, in the creating of these Majorana states on the superconducting system. So with that, I'd like to thank my coworkers, colleagues, and collaborators, and thank you very much for your attention.
Thank you, Didi, for this very interesting talk and for showing us all these super nice results on atomic spin chains. So now we have time for some questions. So if you have any question, you can either just write it on the chat or use the raise hand feature that Zoom has. Yeah, let me. Yeah, so there's a question question already by Andreas Kreisel. Please go ahead.
Yes, I have a question about the first part of your talk, where you showed the Kondo peaks on this chains of manganese and iron atoms, where you have nicely shown that some peak is appearing on one side of the chain. But I saw, if I interpret your figure correctly, that the peak for the two case, yes, this figure I'm referring, that for manganese iron, the Kondo peak is away from the manganese chain, actually.
Yeah, so actually you see that where the atoms are sitting here. So the Kondo peak gets stronger when you move away from this iron atomic side. So it gets stronger for when you are far away from this iron atom.
Yes,
right?
but I mean, I'm referring to the very left one, where the peak is actually in units at 0.72. And this is, if I interpret it correctly, actually away from the chain.
Right.
I would not expect, if you think about just the atoms forming some spin 1/2 state. How, I mean, have you any understanding why the Kondo peak is away from the chain?
Based on my understanding, so it's basically they are forming this electronic state that extend much far away than where actually the atoms are sitting. That this shows this, even though the state, so actually the Kondo peaks are really strong even away from these actual atoms are sitting, right? So I believe that these electronic states that they are making is much bigger than actually the atoms.
I understand, but I mean, if it's bigger, then I would think that it's bigger in both directions. So
both directions,
down and up in this picture. But
yeah,
this is
so
at least unusual. Yeah.
But on the iron atomic side, you see that clearly there's no Kondo features, right? So even though we would measure much further from the iron atomic side, we will not be able to see any Kondo features. So I guess it will be symmetric. That if we imagine to measure much further, let's say almost like 0.7 nanometer in the other direction, we would not see any features. It will be very flat at zero bias, because that's where iron atoms is sitting, right?
Okay.
Thank you.
Yeah, I think Sander has a question first.
Yes, thank you, Peter. So, DJ, very nice talk. I have a question about the last part, these nickel molecules.
Yes,
it went a bit fast, to be frank, but it's definitely a very interesting system. So you showed at some point that in some cases the magnetic moment of the molecule points along the central axis of the molecule and sometimes perpendicular. I was just wondering to what extent you are at this stage certain of this, or to what extent this is speculation, or it's a model. I'm trying to understand how well this system has been identified and studied.
Okay, so this system is well studied on the kappa 100 and kappa 11 system. So it's already there clarified that when you look at this low bias spectra, here, sorry about that. So here, so when you look at the low bias spectra, actually you can compare with the low bias images and the higher bias images, let's say like 100 millivolt bias topography image. And you can see this ring shape, the ring shape here, that which is corresponding to these standing up molecules. So when you compare this image with the low bias image, you can assign that we're sitting the standing up this vertical molecule.
So that's one question. When are they standing up and when are they lying on the side? But then the question is, when does the magnetic moment point along the molecule or perpendicular to the molecule? Because I think I've seen also both, right?
Yes. So we believe that for the standing on molecule, they are lying in this way, right? So the standing on molecule, they are lining parallel to the surface, and the laying down this horizontal molecule, they are standing up.
Yeah, you think that, that's fine. I'm
right.
I'm
So
just
we
wondering,
need to,
how certain are you at this stage of this model, of this explanation?
So yes, for this, we really need to do this spin polarized SCM that we are planning to work on to verify that these spin structures.
Right, I see.
For the
so this is work in progress, but it's definitely very nice. And then at the end, you had this argument about the spin waves. You said that if they're in a nice lattice and a spin wave can propagate, that would reduce the lifetime of an excitation, therefore broadening the peak.
Right.
And I'm not entirely sure whether I understand that argument. I mean, a spin wave state is still a very nice, sharp state, right? It's I don't see why it would have a shorter lifetime. I would propose a different way of explaining this. So as soon as you make a lattice and spin waves can exist, you form a band of spin waves. So rather than having one isolated spin excitation state, you form a band of different, you have different K vectors in the spin excitation that you can excite, and that forms a band, and therefore you see a broadening. I wouldn't necessarily call it a lifetime broadening.
Yeah. That explanation should work also, I guess. Yeah, that they are forming the band structure that makes this broadening.
Yeah, so a spin wave band, right?
Right.
It's just an idea. I'm not sure, but theorists can maybe say more about it. Anyway, thank you for the nice talk.
Thank you.
Yeah, I actually had a question related to what Sander just brought up. So if you deconvolute the spectra, you should get an idea about the line shape. So is it the Lorentzian or something else?
Yeah, this is a Lorentzian.
Okay.
Yes. Yeah,
Thanks.
when you deconvolute it, it shows the Lorentzian features.
Well, Sander asked the question that I wanted to ask about molecules, but I have one more. So regarding the molecular configuration, this seems to be very interesting. Have you seen multi-layer? I mean, the one thing is that at first, the molecular configuration perhaps energetically favorable to sit that way. So I'm not sure if you did any DFT calculation to confirm that. The other thing is about multi-layer. Have you seen any multi-layer for these molecules, and whether the broadening in the line shape also exists or not?
So we haven't tried for the multi-layers. So it's, we only tried like sub-mono layers, yeah, like as you can see here.
And the calculation, the structural configuration for the molecules, the one that, with the rings parallel or perpendicular to the surface. You propose that based on the DFT calculation, just like the total energy of the system is better, or I mean lower, when this configuration is okay.
Yes. Yeah. So
that's the only okay.
From this non-collinear DFT calculation, it shows this spin texture that they couple ferromagnetically for this vertical one, while for the horizontal one shows this fresh things like antiferromagnetic coupling. Yeah. So.
Okay. Thank you.
Thank you.
There's another question by Adam. Adam, please go ahead.
Hi, DJ. Yeah, it was going back to the work on the chromium atoms on lead that you showed, looking at the orbital mapping. I don't know if you can just go back to where you show the orbital contributions of the YSR states.
Yeah.
It was just where you compared the DFT. Yeah, that one you've got there. So I mean, it's just a case like some of those. Oh, yeah, it's going to present you. Some of those, assignments look fairly convincing. So like orbital 5 in negative bias and orbital 4. But of course, a number of them don't look so convincing. And I just wondered if you had any kind of comment as to why sometimes the DFT seems to agree and sometimes it doesn't. Because otherwise, of course, you're just picking and choosing the images that agree and ignoring the ones that don't. And sometimes when they don't agree, it tells you as much about what's going on as when they do. So I just wondered if you had a comment on that, on the assignment there.
Yeah. So we have here this qualitative agreement. yeah, so when you look at carefully, they are not really like exactly same when you compare the simulated YSR states with the experimental one. So the agreement is not perfect, but they have this qualitative agreement. So we have a lot of approximation for these simulated YSR states. Like, for example, taking only the Fermi-sphere and things like this. So what we want to say here, for example, actually this molecule number 4, the simulated simulated whole components of the Shiba states are reproduced here in the electron side in the experiment, and the simulated electron YSR states are reproduced in the experiment on the hole side. So actually, we believe that this molecule, they are having this quantum phase transition. So actually, the interaction between the magnetic atom, so this orbital gets really strong, then they can have this quantum phase transition that they can cross this Fermi level, having this wave function coefficient reversed, right? So this reverse behavior, we believe that they are having this strong coupling of the for these orbitals that makes this reverse behavior. And other than that, the other orbitals, they have this qualitative agreement, not really exactly same, but the approximately.
Yeah, I mean, I guess what I'd argue, you know, to be kind of strong about, like, for example, orbital 1 on the left, I'd say you don't even have qualitative agreement there, because, for example, there's no node or antinode in the center. So in some of the images, you have a clear qualitative agreement. The pictures look the same, but some of them don't. And I just wonder why, you know, if you want to look at it this way, the DFT, you know, quote unquote, fails to reproduce it for some of the orbitals, and whether there's a difference in the way that the DFT simulates some of the orbitals and the others. I guess that was my question. But.
Yeah, basically because this simulation used a lot of approximation that they cannot catch all the features. They cannot catch up all the features that I guess we are missing the features. So my answer is that the calculation is doing a lot of approximation that make the not perfect agreement. I can say.
Okay.
There's another question in the chat, which is why the thermal contribution of U-Shiba-Rusinov states has an orbital shape.
Sorry, what?
Why the thermal contribution of U-Shiba-Rusinov states has an orbital shape.
So why is okay. So basically the YSR states are due to the interaction between the magnetic atoms and the scuba pairs. So how the orbital structure enters. Okay, I will show this. Yeah. So basically, the Hamiltonian of this system can be expressed as BCS and impurity. And impurity side, you can have a lot of vectors that we can get from these orbital structures. So these J's and the alpha and beta. So from DFT, you can put all these input of the U, gamma, and then S. And by by putting these all vectors from the DFT calculation, meaning these orbital structures that the system has, that we can simulate the YSR states. So yeah, the YSR states basically due to this each magnetic orbital that they are forming, and they interact with the Cooper pair individually, separately, that each orbitals can make the individual YSR states, resulting in these 5 pairs of the YSR states in these chromium atoms on lead 1,1 surface. So is it answering your questions?
Yeah, I think so. So yeah, if there are not any more questions, I think that we can start closing the session today. So first, thanks a lot, DJ, for this wonderful colloquium today. It was really nice to see your wonderful results on atomic spin chains. And thank you, everybody, for joining the colloquium today. And remember that the next colloquium will be in 2 weeks from now. So again, thanks a lot for joining today, and see you in 2 weeks.